Thanks, Robert. So before I get into the first drive, I wanted to give a little overview of our mobility system. So if we go to the first graphic, A1, so you'll see our rover during its first drive on Earth. We are a six-wheel drive, so with one motor for each of the six wheels that move us forward and backward. And our four-corner wheels are able to steer, so that's 10 actuators total. But with only 8 motor control cards, we can't drive and steer at the same time. So if we ever want to turn, we have to steer the four-corner wheels in place first and then drive a longer path. So we can turn in place or drive along fixed curvature arcs, and all at a top speed of 0.01 miles per hour. So not very fast. And you'll kind of see those arcs and those tracks when we get into a later picture of the first drive. The wheels are all attached to a rocker bogie suspension system, which has heritage all the way back to Sojourner. And so even though Perseverance is obviously a much larger rover, we're still able to use it. And with our suspension design, we can technically drive over rocks that are about 1 wheel diameter in height while still keeping the rover chassis leveled. I mentioned our suspension design has heritage back to Sojourner. Even parts of our software are built upon code that we've used in previous rovers. So the mobility system that you see today is really built over decades and several missions, with each one making improvements over its predecessor. So some new things that we have on Perseverance are redesigned wheels. They're slightly narrower, they're thicker with a larger diameter, which gives us some better traction. And we have a new grouser design. The grousers are the treads, that tread pattern you see on the wheel, and it makes us less prone to tears in the wheels when we drive over sharp rocks. Another notable new addition to our system is the VCE, which is our vision compute element. If you remember from EDL, we had the VCE for terrain relative navigation. But now that we're on the surface, we've repurposed it entirely for the surface mission to process imagery for mobility and help us with our autonomous navigation. So that same electronics box, because we can't physically change anything on it now that we're on Mars, now has a brand new software installed on it, and it's ready to go for driving thanks to our incredible VCE team. So that was just one of the things that we did in preparation for our first drive. If we go to our second graphic, A2, we also did a sphere actuator checkout. So I mentioned each of our four-corner wheels are able to turn. We commanded each of those 4 wheels through a 30-degree range of motion while monitoring motor performance and suspension angles. And it went really well, in certain cases better than we expected. We saw some performance that in some cases was better than we've seen on Earth driving in the Mars yard. And whether that's from the underlying terrain or, the Mars gravity, we're not entirely sure, but it worked beautifully, and we were so excited to move on to the first drive. So if we go to A3, you'll see what our first drive actually did yesterday. So our plan, which executed perfectly, was to first drive 4 meters forward, that's about 13 feet, make a 150-degree turn to the left, counterclockwise, and then back up about 2.5 meters, about 8 feet. And then during that drive, we took a pause to image the touchdown contact patch on the tires. So where the tires made contact, or the wheels, I should say, where the wheels made contact with the ground when we landed. And also throughout the drive, we took some images from the nav cams and processed them on our VCE to kind of prove that software pipeline that feeds images into the VCE for perception and image processing. So our first drive went incredibly well. If we go to A4, you can see the wheel tracks that we left on Mars. I don't think I've ever been happier to see wheel tracks, and I've seen a lot of them. And this is just a huge milestone for the mission and the mobility team. Like, we've driven on Earth, but driving on Mars is really the ultimate goal. And just so many people I can't even count have worked towards this very moment for years. Whether they worked on designing and building the actuators, the newly redesigned wheels, the motor control system, writing this incredibly intricate mobility flight software, or spending days and nights in the test bed in the Mars yard, testing, debugging, or retesting the mobility system to make sure everything works together. Like, this is really what we've been working towards, and it's just amazing to see. I don't think the team could have been happier. So, looking ahead, we're going to do some longer drives. This is really just the beginning. Now that we've showed that we're able to drive and we can do this, our mobility system is capable of doing so much more. We still drive at 0.01 miles per hour, same as Curiosity, but thanks to our improvements on our AutoNav software, our enhanced navigation software, and our new cameras, we can really drive 5 times faster than Curiosity, and we're capable of averaging about 200 meters per stall. And that's also partially due to the VCE, which offloads the burden of image processing from the rover's main computer. We're able to think while driving. So in other words, Perseverance can walk and chew gum at the same time, is a phrase we kind of like to use. And so we're able to take a stereo pair of images, process those images on the VCE, identify hazards in the terrain, and choose a safe path forward, all while the wheels are still turning and moving forward. And so this means we can drive longer in the same amount of time, and we can have less time planning drives and driving on the surface, which means more time to do science, which is why we're there in the first place. And speaking of science, I will hand it over to Katie to talk about what the science team is so excited to do with all the extra time they're going to have.
Thanks so much, Anais.